Hello all of you. Welcome to the 33rd lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing numerical methods for solving equations. We started from the linear and nonlinear algebraic equations, and we discussed different methods for numerically solving those equations and how to implement those solutions in Python. Right? I will take it forward the discussion now talking about multiple nonlinear equations in particular and see like how we can solve those kind of equations. So, as we discussed towards the end of the last class, that if we have multiple equations in multiple variables, we need to write the equations in a vector form where x is now a vector of unknowns x1 to xn if we have n equations, and then f of x is a vector of the functions f1 to fn. And we discussed and we gave example of a case when we have linear equations. In that case, it becomes quite easy. We have equations in the form ax equal to b, and then we can use standard matrix algebra to compute the matrix inverse, because the a and b are basically having constants, so it becomes fairly straightforward, right? But what if the equations are nonlinear? In that case, clearly a and b are not going to be constants, and we have to think about other methods of solving those kind of equations. So, the first thing that we can do is to extend the idea whatever we had for the direct substitution for many variables, right? So, just to recall, we wrote the equation in the form x equal to f of x, and then basically I started with some guess and got the new guess by putting it into the function. So, x new became function of x old. So, I want to extend this kind of an idea to multiple variables, right. So, very first thing what we will do, we will write whatever equation that we have in the form x equal to f of x, where x is the same unknown vector, but now this function vector is appropriately modified, right. And then we perform the same kind of a iteration that we did. So, the value of this vector now in the k plus 1th iteration is the value of the function vector for the previous iteration value of x, and we keep on doing it until the error becomes less than tolerance. And now it is time to define a more formal definition of the error. We define in terms of the norm of that vector. So, whatever is the new value minus old value, that becomes a vector, and for a vector I can define a norm, and I can define the norm in multiple ways, but in general the definition is something like this, where p can be any number, and if p is equal to 1, essentially what we are doing, we are summing up the absolute value of the difference, something like x1 new minus x1 old plus the same thing for the second variable, right, and the same sum for all the n variables. If I sum up the absolute values, then I get what is known as the 1 norm, and 2 norm is going to be the sum over the squares, right, and that is more commonly used. It gives like a distance kind of a function, and that is why it is used a lot, right. So, we have a definition of error which we have already used, but this is a more formal definition of the same error value. Okay. But then I can apply the same logic on the Newton Raphson method. We have the method for one variable, why not extend it to multiple variable, right. Just to recall, the equation went like x new. For one variable we had like this, x new is x old minus function of x old by f prime of x old. And if I simply blindly replace all this x with the vector, I will have something like x new, which is now a vector, is equal to x old, which is now a vector, minus the function vector of x old divided by the derivative of the function vector of x old, right. So, we do not know how to divide vectors, right. So, we cannot divide a column vector by another column vector. So, clearly this is not the correct extension. The correct way to extend that is by defining some kind of a Jacobian of this, which is defined like this, right. So, basically I can reframe the earlier equation as something like my delta x, which is a change in the x, is my minus f of x by f prime of x, and I can move it on this side and I will get f prime x del x is equal to minus f of x, right. And now if I have to extend this to multiple variables, I will replace this f prime with a Jacobian, which is now a matrix of the derivatives, and that is equal to minus of the function vector, right. So, basically I rewrite the equation in this particular way, and now I replace this f prime with the Jacobian, and now since Jacobi is a matrix, so therefore I have to dot product that with a column vector of delta x, and that is equal to minus of the function vector, right. And this Jacobian is defined as something like this. So, you have n into n matrix. The first row are the derivatives of the first function f1 with respect to first x1, then x2 until xn, and along the columns we are doing derivative with the same x1, but now changing the function dou f1, dou f2, dou f3 to dou fn, and then similarly for the second column we will have x2 in the bottom and so on, right. Why we are doing this, right. So, this again comes from the Taylor series. So, just like the Taylor series for single variable function looks like this, if I do have to extend it to multiple variables, then in that case I have to redefine it in a certain way, right. So, let us say if I have now a function of x and y, so then I will have step size or the increment in the x direction, and then same for the variable y, or you can say y direction if we prefer, right. So, we will have x plus h and y plus k, and that is my function value at x and y. And now we do not have a single h, we have now two steps, right, h and k, h for x and k for y, right. And we do not have a single derivative also, we have actually two derivatives, one with respect to x, other with respect to y, right. So, we can write it something like h into f of x, which is the derivative with respect to x, plus k derivative with respect to y, right, and so on, right. I am not writing the higher order terms, right. So, now we have two terms appearing here, one that contains the derivative of function with respect to x, and other that contains the derivative with respect to y, right. And if I now want to write it formally, I can write it something like h k multiplied with something like f x x y. In fact, I have to do the opposite of this. So, this will be something like this, right. Now, let me write the same thing in the Jacobian terms, right. So, in that case the Jacobian becomes a matrix something of like this, right. But what we also need to keep in mind is now we have in fact two functions, right? Because I am now solving for two variables, so now I have two functions. Now let me call these two functions as f and g. So in that case, I have another function g x plus h y plus k, and that is equal to g x y plus, again I can apply the same logic, we have h g x plus k g y, right? And now you can see I can use the idea of Jacobian, right? What is going to be my Jacobian in this case? The Jacobian is going to be something like this. My first function is now f and second function is now g, and my first unknown is now x and second unknown is now y. So I can define my x vector as x and y, and this is going to be something like fx, fy, gx, gy, and therefore j dot delta x is going to be fx, fy, gx, gy into delta x, delta y, and that I am setting equal to minus f of x, minus f of x, and that is equal to minus of f and g, right? So if I plug it in there, so I am going to get something like this: minus of f and g is equal to fx, fy, gx, gy, delta x, delta y. By the way, delta x, delta y is my h and k if I prefer, and that becomes minus of f g is equal to h fx plus k fy, and then at the bottom we have h gx plus k gy, which is precisely the terms that you see here, this term and this term, right? So the key idea is that when we have two variables x and y, then we will have two functions, and therefore we will have a function vector f and g, and then therefore we will have a delta x vector, a column vector, right? And if I now do a Taylor series, right, so I am going to have derivative with respect to x, with respect to y, and if I combine those, then I get the form whichever I have shown in there. Okay, so that's exactly what we do here. So we have this. Now the main, I would say, interesting aspect of this is that when I look at this Jacobian, at first glance it seems to be quite complicated, but I am evaluating the Jacobian for a given value of the x. I am doing it for the old value of x. So I know all the derivative, provided I know the expression of derivative, I can plug in the value of x and I can get all terms of the Jacobian, and they are therefore going to be constants, right? So this is going to be a constant matrix now. The function vector also is evaluated for the old values of x. So this also becomes a constant vector, right? So now we have something in the form a delta x k is equal to b, which is now in the linear form, and therefore I can solve for this delta x k, right? So every step of the solution of this scheme, I am basically solving a linear equation, right? As I said, in the one variable case, if we had a linear equation, Newton Raphson method will give you the exact solution in one step. The same is going to happen here as well. We will have a linear equation for something like this, and we will get the solution in one step. If it is nonlinear, I will get the increments in the unknown vector after one step, and then I will keep on doing iteration, right. But in every step I am solving a linear equation, and there are methods to solve linear equation. We can imagine that linear equations are easier to solve, and therefore we don't worry about that, okay, or worry less about that, right. All right. So, let me now take an example, and we will look at a triple effect evaporator, which having a forward feed. This example we have done long back in this course, but just to recap, basically what we are doing in a triple effect evaporator is the subsequent effects after the first effect is powered by the vapor coming from the previous effect, right. And in the forward feed, the feed and the fresh steam both enters the first effect, right. So, feed is my F, I am talking in terms of the mass per unit time of the feed, and at some temperature and some mole fraction of the mass fraction of solute, and then there is a fresh steam, again mass flow rate, mass per unit time S, at some temperature, some pressure, both enters the first effect, operating at some pressure, some temperature P1 and T1. What is key is Ts must be higher than T1, and it has some area. Let us assume that it has some heat transfer coefficient for the heat exchange U1. Now, whatever V1 the vapor comes out of this, it is used to heat up the subsequent effect, second effect. So, the second effect is not getting fresh steam, it gets the vapor from the first effect, and this liquid that leaves the first effect becomes the feed to the second effect, and this continues for the third effect. What is important here is P1 is higher than P2, higher than P3, and T1 is higher than T2, higher than T3, right. If you want to learn more, you can go back to the lecture on evaporators, where we have discussed this in much more detail. Okay. So, for this particular case, we have derived a set of equations. I have kept aside the solute balance because they can be solved separately. Fxf is L1 xL1 is equal to L2 xL2 is equal to L3 xL3. This can be solved separately, right. So, these solute fractions are not appearing in the other equation. So, therefore, I am not worrying about these. This can be done separately, and they are easy equations to solve. I am worrying about the three energy balance equations, right. One thing is important here, that I have already substituted for the V1, V2, V3 using the material balance, the overall material balance, right. I already have done that. So, basically there is a sensible heat change for the liquid that comes inside the evaporator effect. Then there is some energy given by the steam or the vapor in the subsequent effect, and that is equal to the energy that is going out in the vapor leaving the effect, right. That gives me the energy balance equation. And then we have three heat exchange equations, where basically the energy supplied by the steam in the first effect is S lambda S. In the second effect, it is powered by the vapor V1 leaving the first effect, and V1 is equal to F minus L1 from the material balance. So, therefore, this is the energy coming, and that is equal to UA delta T, that is U2A T1 minus T2, the temperature difference, and the same is there for the third effect. Again, you can always go back to the lecture on evaporators when we have derived these equations. And let us say, just for sake of argument, some given values of the unknowns. So, these are the mass flow rate F, different temperatures, the liquid leaving the last effect, and the property values are also given. In general, latent heats are a function of temperature, but in this example I am taking it to be constant, and U1, U2, U3 they can be different, and I have taken different values, but in the example that I have did in the evaporators, I have considered them to be like same for all the effects. Okay, so let us say if these are the 6 unknowns that I have to get from these 6 equations. We have discussed a Bazar-Maccabi method that basically assumes T1 and T2, and then we get areas A1, A2, A3 from equations 4, 5, 6, and then we solve 1 to 3 to get other unknowns, and then we keep on iterating until the areas become equal. That was the Bezer-McCabe method. But I want to take a separate route now. I will apply the Newton Raphson method, whichever we have developed for this particular case when we had the evaporators. Okay. So this is my function vector and this is my unknown vector. So you see I had 6 unknowns, I have put it here. So S becomes my x0, the 0th element, T1 becomes x1, T2 becomes x2, L1 becomes x3, and L2 becomes x4, and A becomes x5, the 6 elements of X. And now when I write the function vector, essentially I wrote these 6 equations all in the fx equal to 0 form. So basically the right hand side goes to the left hand side, so that the net final right hand side is 0. That's what I am doing. And what I am also doing is whenever I have an unknown variable appearing in the equation, I write in the notation of which element of X it is referring to. For example, we have FCP TF minus T1. FCP and TF is known, but T1 is unknown, and T1 is the first element of X, right? That's why I put X1 here. The next term is S lambda S. S is an unknown and it's a 0th element, so I put X0 here. Then F minus L1 lambda 1 comes here, and L1 is the third element here, so I put an x3 here. And the same thing I did for the second equation, L1 Cp T1 minus T2. L1 is my x3, then we have x1 is my T1, x2 is my T2, and then here again we have L1, right? And the same thing I have done for all the equations in there. So essentially I wrote in a manner that my function vector of X that gives me, like for unknown values, it gives me which X element I am referring to, and for all the known variables I am using it in the symbolic form, right? This will make it easier to code. All right. So now we can go ahead and compute the Jacobian, right? So Jacobian is going to be the derivative. So in general, my Jacobian is dou f1 by dou x0. In programming notation, we always start from 0. That's why I am calling it 0. And then we have dou f0 by dou x1 until dou f0 by dou x5, and this continues downside also, and in the end we have dou f5 by dou x0 until dou f5 by dou x5. Just see how we are computing the Jacobian term. So the first term is dou f0 by dou x0. F0 is right here. This is my f0. I want to take a derivative with respect to x0. Everything else is constant or not a function of x0 except the second term. So when I take a derivative with respect to x0, I am going to get lambda s as the first term. The next term is the derivative with respect to x1. We have to locate where is x1 in this equation. It is right here. So I get minus fcp as the second term. Then the next term is x2. x2 does not appear in the first equation, so I have a 0. x3 appears in the last term, so I get a lambda 1. x4 does not appear, and x5 does not appear, right? So you can compare. This is my first row, right? Now for the second row, this is my f1. First, I take a derivative with respect to x0. x0 does not appear here. So, the first term here is 0. The second term is derivative of f1 with respect to x1. x1 appear here. So, we have x3 Cp coming here. Then the next term is derivative with respect to x2, and you see accordingly we will have x3 Cp, but with a minus sign coming here, and so on, right. So, let us go ahead and write the code for this problem, right. So, again I have done Python earlier in this class in the previous lecture. So, let me go ahead start showing you the code. So, I am using few libraries, right. So, we am using some NumPy library for some functions, and in NumPy I am also using a linear algebra solver, because ultimately I have to solve this equation j dot delta x is equal to minus f at every step of my Newton Raphson code. So, I give the input variables whatever is specified in the problem. So, all these variables have been specified in the problem. I made sure that the units are consistent, right. You have to always check that, and I plugged it in there, and then this is where I compute the function vector and the Jacobian vector, right. And now you see why I have written the function in that particular manner, right. So, my function vector is a function of x, right. So, I will pass to this function the value of x, that is my x at a certain iteration, and it will return me the function value for that value of x, right. That is the reason why I have written the function vector in this way. So, I wrote x0, x1, x2, because these will come from the x value which I am passing to the function, right. But essentially it is the same thing whatever I wrote here. Let us compare the first term, for instance, FCP TF minus x1. So, we have FCP TF minus x1 plus x naught lambda s minus f minus x3 lambda 1. So, we have plus x naught lambda s minus f minus x3 lambda n, and then similarly for the other terms there. And now we also put the Jacobian. Jacobian is also a function of x, and we already have computed the Jacobian. It's just a matter of inputting inside. So, let us for example compare the first row, lambda s minus FCP 0 lambda 1 0 0. That is exactly what I had here, lambda s minus FCP 0 lambda 1 0 0, right. So, the same kind of a thing I do for all the 6 rows of Jacobian as well. So, these functions have been defined. I have still not written the actual iteration code, but if I pass the x value to these functions, they will give me, this will give me the f, and this will give me the corresponding j. All right. Let me now start writing the actual Newton Raphson code. So, I need some initial guess of x that has to be basically having 6 elements. So, I gave some initial value, and the initial value in fact is very important, because if it is too far from the true solution, it is probably not going to converge so easily, right, and things can get complicated. But there is no way you can guess so easily what is my final solution. But if you have some reasonable guess based on the understanding of the system, that really helps to converge the solution faster. And then, as I have said, just to get in the loop for the first time, I have defined some error value and some tolerance value where we will stop when error is higher than tolerance, right. And if it was a better code, then I should also have a maximum iteration feature, but in this case I am kind of sure that it is going to converge. So, therefore, I am not putting it, but as a good matter of coding practice, it is not a bad idea to also have a limit on the number of iterations. That we can do by including one more condition here, and let us say count less than 1000. Okay. And then what is essentially happening here in the code is very simple. So, we are solving the equation j dot delta x is minus f. This minus f I am calling some vector n f, and that is solving using a solve function that takes this j and the function x, right? That takes this j and the function f, and it gives me the negative value of delta x, right? So basically what I am doing here essentially is I am doing like this: j dot minus delta x is equal to f, not the nf as I just said, right? And I am solving for minus delta x, right? So it is of the form ax equal to b, where in our case a is equal to j, x is equal to minus delta x, and b is equal to f. So the solve function takes essentially as input a and b, and it gives me the output as x, which in our case is minus delta x. And clearly once the norm of that minus delta x that becomes very small, I want to stop. So we define the error as this, right? The way I have written, the norm function automatically computes the 2 norm, that is for p equal to 2 value, whatever I have discussed earlier, right? So I have given you the equation of the error. So this will compute the 2 norm p equal to 2 if I use the norm function. All right, and then I want to do essentially the new value of x is the old value plus delta x, but I have solved for minus delta x. So this is going to be x old minus my minus delta x, whatever I have computed, right? And then I keep on doing it until my error becomes less than the tolerance, right? So you can see we get a solution in like 10 iterations. That's quite fast, and this is the final function value. In fact, it should be pretty much 0, but then I mean it's a numerical scheme, so we don't get to 0, but you see the values are fairly small, and these are the values of the unknown. So this is my s, this is my t1, this is my t2, this is my l1, this is my l2, and this is my a. I can do few consistency checks here. For example, my t1 must be higher than t2, which is indeed the case, and t1 must be less than ts, which is also the case because ts is defined to be 120, and my t2 must be higher than t3, which is also the case because t3 is 50 and I am getting t2 as 82. So my solution is kind of consistent, right? And therefore we can rely on this solution. Of course, none of the x values are negative, which cannot be because temperatures, the flow rates, they cannot be negative. So just before we close on any numerical problem, it's a good idea to check whether it is making any physical sense or not. So going forward, there is one kind of a linear problem that also is encountered a lot in chemical engineering, and therefore we will discuss an algorithm for a linear problem where the A matrix, that is my coefficient matrix, I have told you that the linear problem is Ax equal to b, where A and b both are containing constants only, but there is a particular case in there where the A matrix only contain terms along the diagonal of the matrix, then what is known as the upper diagonal, and what is known as the lower diagonal. Now for this kind of a problem, there is a method called Thomas algorithm that works in the following way. What we do here is, in the first step, we change this matrix into a matrix like this, where we don't have the lower diagonal, we only have the upper diagonal left, and that step is called the forward elimination step. And I will give you examples of how it is done. So you can go back to this matrix and let us see what equations does it result in. So the first equation is coming from the first row multiplied with this column, and that gives me b1 x1 plus c1 x2 is equal to d1. I can rewrite this equation as x1 plus c1 by b1 x2 is equal to d1 by b1. And now the second equation, that is going to be something like multiplication of this, that is a2 into x1 plus b2 into x2 plus c2 into x3 is equal to something like d2, and I am basically again dividing it by b2, and I get something like x2 plus c2 by b2 x3 is d2 by b2 minus a2 by b2 x1, right, where x1 can be gotten from the previous equation, right. So this is what is known as the forward elimination, right. So I am getting x1 from here, and this is called the forward elimination. Now once I have done for this, I can go to the next line and I can get x3 as a function of x4 and x2, but x2 can be gotten from the previous step, right. So basically what this amounts to is I am now getting a matrix something like this, where it does not have the lower diagonal, right. And of course the coefficients are also modified, as I showed. For the first equation, we had coefficient as c1 by b1 and d1 by b1, that is exactly what comes here. And for the following one, we are doing an elimination, so therefore this term is also appearing in there, right. And of course the q, that is the right hand side, is also modified appropriately. It turns out that we can go ahead and now do a backward substitution. So what I have done so far, I have gotten rid of this lower diagonal, and now I can get rid of this upper diagonal by basically going backward. So I start from the last equation, that gives me xn is equal to qn, and now I can go to one step above, and I will have, for the second last, I will have something like this: xn minus 1 plus pn minus 1 xn is equal to qn minus 1. But you already obtained xn equal to qn from the last equation, so I can plug it in there, and I can get xn minus 1 is equal to qn minus 1 minus pn minus 1 qn. And now once I have got xn minus 1, I can go further up and compute xn minus 2. So basically we are doing two steps. One, we are doing a forward elimination that eliminates the lower diagonal, and then we are doing a backward substitution that effectively eliminates the upper diagonal, and then we have a solution of this algorithm. It turns out that we can extend it to something known as a block tridiagonal matrix, where every element of the matrix is in fact not really a scalar value, but actually a matrix, right. So I am showing an example here. So this matrix, it is clearly not a block, it is clearly not a tridiagonal matrix itself, because you see the diagonal is of course non-zero, but apart from the upper diagonal and lower diagonal, there are many other elements which are non-zero. So it is not a tridiagonal matrix, but it is a block tridiagonal matrix if we consider that every element is actually a 3 into 3 matrix itself, right. So if I can consider this 3 into 3 matrix as one element, then essentially every element here is something like this. And now you can see that if I look at the diagonal here, the diagonal contains the matrices having non-zero element. The lower diagonal now is this diagonal, which also contains matrices having non-zero element. The same is true for the upper diagonal. But then, apart from that, what is left with are the matrices containing all 0. So, we can extend the idea of tridiagonal matrices to a block tridiagonal matrix, where every element of the matrix is not a scalar value, but it itself is a small matrix, right. So, in this case, that small matrix is a 3 by 3 matrix and the big matrix is a 9 by 9 matrix, right. And again, I can replace the coefficients now with vectors and matrices, just like when I looked at the extension of Newton Raphson code. So, I went from scalar value to vectors. The same thing I am doing here. Now, my coefficient matrix contains basically matrices, right, and we have vectors appearing here, and I can essentially extend whatever I had for tridiagonal matrix to what I have for a block tridiagonal matrix using very similar ideas, right. So, this looks quite straightforward coming from here. Keep in mind, now Pi becomes a vector. So, to get a scalar quantity, we have to, Pi becomes a matrix. So, to get a vector from this, we have to dot with another vector, right. But in here I had a C1 by V1, but now if C1 and V1 becomes vector, we cannot do a division of vector. So, what we do? We do something like B1 inverse C1, and similarly here we have B1 inverse D1. That is pretty much what we can do. And this also I want to do an inverse of that. That is precisely what we have done here, and we have put a dot product here because I want to get a vector. AI is a matrix and Pi minus 1 is also a matrix in this case, right. So, I can go ahead and basically extend the code in this particular way, and I can get basically an extension of whatever we had for the tridiagonal matrix to the case of a block tridiagonal matrix, right. So, with that I conclude the discussion, but before that we can also see that we can do a backward substitution, and again that is again based on the extension of whatever we had for the tridiagonal matrix. I am simply changing the variables by a vector. So, with that I want to conclude this lecture. In the next lecture, I will talk about how we can solve ordinary differential equations by a numerical scheme. Thank you so much.